Okay, can you hear me? Please raise your hand.
Push present mode again. We can hear you all the time.
Can you hear me, Gadi? Please raise your hands.
We hear you. Just press present. Make present again. Are you presenting now? Go ahead. You can go ahead. Continue.
Gadi, can you hear me? Please raise your hands.
Yes, we can hear you. Go on.
Go on. Okay. So the first rule is when testing under an existing structure is to lower your expectations. The pulse echo method is highly affected by the waves from the superstructure. Note that when you hit the pile and you're creating a compressive wave going down, the same wave also travels up into the superstructure, and it can be reflected from any edge. It can be reflected from the ceiling or from the side of the beam. It can go sideways, upwards, anywhere. Moreover, the wave going into the superstructure is not attenuated as much as the wave going down. And there's no way of telling what the waves are doing in the superstructure. It can be very misleading. For that, more than one pile, ideally many more, should be tested so that we can check repeatability. The assumption is that the piles are going to generate a unique signal, while the superstructure at each location is going to generate something different. So that if we do get a repeatable result, we can assume with some certainty that it is really the pile and we are not just testing the ceiling or the beam. Never trust the results of just one pile. The only real expectation here is the length of the pile. We don't get much more information, if at all. To summarize, we recommend to try. If it works and we get reliable, trustworthy information, great, because the alternative is much more expensive and slow. It's very hard to get.
Disturbing you. Your PowerPoint is not so. Is not seen here like before.
What is?
Maybe you should
press present mode again.
I'm sorry?
Press the present mode again.
Gadi?
Just a minute.
Can you hear me? Please raise your hands.
We can hear you. Just press present mode. Are you in present mode? Let's go.
Yeah, press this. No, this.
Okay, can you hear me now?
Keep on going. Now it's okay.
Okay. Let's go.
Yes, keep going, Mr. RS.
Okay, perfect. Thank you. Thank you, Yono. It's helpful. Okay, the next testing method we're going to discuss is the ultrasonic testing, cross-hole ultrasonic testing, also known as CSL. Let's just give a very, very quick overview of the cross-hole testing, and then we're going to see also a 3 minutes video. So for the cross-hole testing, at least 2 access tubes need to be installed or drilled into the pile. And then the test apparatus and the computer is going to be connected. We're going to lower into the tubes, which are going to be filled with water, a transmitter and a receiver with cables. The cables are going to go through our depth meter into the recording device. And while we pull the emitter and the receiver together, an ultrasonic wave is going to be transmitted. And we're going to measure the time of arrival and the energy as we pull. So let's see a short video to demonstrate that. It's a 3 minutes video.
On this site, large diameter board piles were constructed. On the surface, they all look perfect. But are they? CHUM, compatible with ASTM standard D6760, looks for the subsurface imperfections through the access tubes installed. Depth meter pulleys are placed on top of the water-filled tubes. Ultrasonic dual-function transceivers are lowered into the tubes. And lowered together all the way to the bottom, which may be 100 meters below ground level. When the sensors are level, the computer connected to the CHUM gives the order pull. While both cables are pulled together, at a speed as fast as 2 meters per second, the location of the sensors is shown on the screen in real time. Ultrasonic pulses are continuously sent from the emitter to the receiver, and anomalies, such as increased arrival time or lower energy, are immediately displayed. CHUM automatically adjusts signal gain for optimal signal quality under variable conditions. CHUM also supports 2D and 3D tomography. Both sensors exit the access tube together, and the ultrasonic profile is already on the screen. First arrival time, relative energy, wave speed, and the waterfall presentation. Other profiles are logged the same way. The data is analyzed by the engineer who checks for any inconsistencies, adds his comments, and prints the report. This, in short, is the CHUM, our cross-hole ultrasonic monitor. It is portable, rugged, and productive. Due to the use of a detached computer, the CHUM will never become obsolete.
Okay, so now that you have some basic understanding about the cross-hole testing, how can we adapt this test method for testing under an existing structure? And here it becomes very tricky. Since the top of the pile is not accessible, our only option is to drill several cold drilling through the superstructure into the pile throughout its length. This is hardly ever possible or practical. However, if we're talking about very expensive piles, very massive piles, and a critical superstructure, this might be the only option. When we do manage to do that, let's just talk about that point for a second. To drill a vertical hole into the pile throughout its length is going to be very challenging. First of all, it's hard to keep the course vertical. And second, we have no information if the pile in the first place was vertical. And what happens is that in most cases, after 10 or 15 meters, the VIDIA core is going to cut the spiral and the reinforcement and go outside of the pile. So that would be what's going to happen in most of the cases. It's also very expensive. So to summarize, although it's really a very, very good test method with really high resolution, it's almost always impractical for testing under an existing structure. But I do want you to keep it in the back of your mind that this option exists for very special cases. In these cases, the quality of the test is going to be very high. The superstructure will have zero interference with the test. The third test method we're going to discuss is the parallel seismic method. STM standard of this method, as I wrote, is already in final stages, will be ready within a month. So the parallel seismic method is set up like that. If that is the pile and the superstructure, we need to drill a parallel access tube all the way down to the bottom of to the expected length of the pile, and at least 5 meters more. The tube must be non-metallic. It must be as close as possible to the pile. The soil should be saturated to pass the waves, and the tube should be filled with water. Once we have this set up, we lower a hydrophone, like a water microphone, into the pile, into the pipe or the access tube, in parallel to the pile, and we hit the pile or the superstructure in any location, as long as it's uniform. We have to hit the same location every time. As we hit, we lower the hydrophone in fixed intervals, and whenever the microphone is still parallel or in front of the pile, the wave speed that we get, the arrival time, is going to be represented by the speed, by the wave that travels through the concrete. Once the hydrophone passes the toe of the pile and starts going into the area of the soil, the wave speed that we're going to get is going to be the wave speed in soil. And we're going to catch this breakpoint in the wave speed. It's going to look like that. So this is an actual parallel seismic result. And let's analyze that. On the vertical scale, we see a depth starting from 0 going down to 30 meters here. Horizontal x-axis is the time, and we can see the pulses here. So the top 8 meters here were simply not saturated enough to pass the waves, and we simply ignored them. And then we can see that the waves keep getting farther and farther, later and later, and the slope here is about 4,900. This is a typical velocity for very good concrete. Once we passed a certain point, the slope of the arrival times becomes much more relaxed and much lower. And if we do a linear regression of this part and this part, the crossing point of the two represents the end of the pile. So we can get an 18 and something meters length pile. That's basically the parallel seismic method. The resolution that we're going to get, the accuracy that we're going to get is approximately 1 meter, and it depends on many factors. I want to emphasize that the parallel seismic is designed for testing under existing structures. With all the shortcomings, it's still the only method which is designed just for that. Note that a parallel access tube must be drilled, it must be non-metallic, the soil must be saturated, the strata should be uniform. If we have many layers or a rock, it's probably not going to work. The accuracy of this method is going to be affected by many factors. But still, it's probably the best method for testing under existing structures, albeit slow, relatively expensive, and limited. Note that the only information you're going to get is length, nothing more. So we've gone all about around the three testing methods that we offer for this scenario: the pulse echo method, the cross-hole ultrasonic, and the parallel seismic. Now, I was told that some of the slides about the pulse echo methods were not heard well or visible. So if anyone wants me to repeat that, please use the raise hand button on the bottom, or write that on text, or simply raise your hand in video so that I can see that before we go into the conclusions. Okay, I don't see any hands. Okay, no hands raised.
מישהו ביקש, ביקש לבדוק את זה. אתה לא רואה? זה כזה, זה בתוך מים.
Okay, how am I going to show that to everyone?
I don't know, but...
Okay, and how am I going to show that to everyone?
We can go like this.
Let's see if we can see that. I doubt that.
No, I'll try and show it. But present the part with the pet. How do you test with the pet?
Okay. There was an interesting question, and we're going to go back to that. We have some time for questions, and I'll do my best to answer. Let's go into the conclusions, and feel free to ask your questions at any point now. So first, this conclusion slide is here for scaring you. Testing under existing structure is really not desired. It should be your last resort. When there's no other option, this is the only way to go. But it should never be designed. So the piles should never be designed to be constructed, then some superstructures, and then testing. Design should always be to test the pile before any superstructure is attached. The results of testing under a structure should not be trusted too quickly. A lot of solid engineering judgment must be applied, because when you compare this kind of testing to testing under to normal testing, then you have a fewer test methods in your arsenal. You have fewer options. Less information can be obtained, usually just length, but nothing about integrity or defects. The test is going to cost you much more, and you're going to end up with a lower certainty. I just hope this is clear to everyone, and I managed to scare you away from testing under existing structure, unless this is your only option. Video?
No, not a video. בודקים בתוך under structure.
Okay, I was asked to go back a few slides to show you how actually the pulse echo method is going to be adapted to testing under existing structure. So hang on a second. Okay, so here we go. So how do we adapt the pulse echo method to test under existing structure? I'm going to get over that very quickly for those who did get it. So when the top of the pile is round and the column is square, we can sometimes get some kind of a notch there. For example, here, in this case. Can you hear me, everyone? Can you see the slides now?
Yes,
Okay.
Yeah.
Of course.
We can test here. Great. In this case, we have some access here to the top of the pile, or here. The other alternative, if we don't have access to the top of the pile at all, is to cut a small notch at the side of the pile. Like in this case, this is a part of a retaining wall, and this notch was cut into this pile. Here's another example with the sensor inside, so you can see the side of the notch. It's constructively neglectable compared to the size of this pile or column. And in another case, another pile in a retaining wall, and a small notch was cut there. You can see the hammer for proportion. This gives you the good option for testing with the pulse echo method. Okay, and
Anyways, we have one.
thank you. I'm really looking forward to hear
Just a
your
minute,
questions.
Anyways, yes. Someone asked how to test.
Hang on a second. I can hardly hear you.
Someone asked how to test under some specific structure. He brought in a picture, so I'll try to present the picture. Let me see.
Sorry, I cannot hear anything.
You can't hear anything? Can you hear me now?
Yes, now I can hear you, but let me move to.
Yeah, just a minute. Let me show.
Yeah, let me put this on. Speak now.
Yes. Okay. Can you see the picture now? Can you see the picture?
Let's close this the presentation and go to video. Neto.
Okay. Now
Yeah.
you see
Okay, I can see the picture very well.
Okay. So he asked how to test this in this case.
Okay, so what we see here is something we have no idea about it. We have no idea if there is a single monopile under this massive head, or a group of piles. It can be a footing. The first thing that I would do is detective work. We have to apply all the information retrieval that we can in order to find the engineer who designed that, to know what was done there, even if that was done 30 years ago. We can still find some records. We have some veteran engineers who can tell us what was the common construction those days, what were the available augers, drilling machines on those days, what was the common practice. If we have some kind of a project nearby, we can try to find out what was done on that project, and from all this we can get some educated guess, a guesstimate about what's expecting us underground. Of course, every project is different, everything is different, but if 30 years ago we wouldn't have a drilling machine that can go below 30 meters, then that's probably an upper limit. A detective work like that is going to be much cheaper than starting to test, and it's like a literature survey. So once we have all this, the best guess that we can, assuming these are actually several piles under this head, I can see that drilling from the top is probably impossible, and that this pile is probably quite massive. So a pulse echo method will probably not work. A parallel seismic would be the only alternative. A drilling machine needs to be positioned somehow, and an access tube needs to be pushed at least 5 meters below the expected length, and then parallel seismic would be the only way to go.
Okay, so basically, you're saying is that you need to find a way how to drill in the water a parallel tube to be able to do a parallel seismic test for this.
Correct. And please note that the access tube needs to be as close as possible to the actual piles. Let's say 1.5 meters would be an upper limit. So that's going to be tricky here, but it's still possible. As I told you, it's not an ideal case. It would be much better to test the piles before the head was made. But I guess that's the only alternative right now. By the way, if this is a new construction, there would be a record of the piles. And if someone wants to test the integrity of the piles under these superstructures, that's over-expecting. There's no way to test integrity of the piles under that. We can only learn about the length.
Okay.
Any more questions or similar pictures to send, guys? Okay, so I'm going to pass the presentation to Mr. Zulfriki, who's going to say some closure notes.
Mungkin ada pertanyaan mungkin, Bapak-Bapak, Ibu-Ibu. Ada yang mau bertanya, silakan.
Oh, yes. Okay, I can see some. How can I see the questions?
No, there's no questions. They only
No
have
questions.
on the messaging board, yes.
Okay, so unless there are some closing notes from Mr. Zulfriki.
This is a question. What information could we get from this test method, each of these test method?
Okay, so let's repeat this. From the pulse echo method and from the parallel seismic method, in this scenario, we can only learn about the length. Although the pulse echo method can give you much more information if there is no superstructure, in real life, the expectation is only to get length when we have a disturbing superstructure. If we manage to drill access tubes throughout the length of the pile or access course, then the cross-hole method can give you exactly the same information as ignoring the superstructure, because the sensors are going into the pile. So in this case, we can get a very high resolution about any defect in the pile. Of course, as I told you in the presentation, this is an unlikely case, which is only applicable to very, very massive and expensive structures, like the one that we just saw in this picture. This might be a candidate, a coring machine on top of that structure. More questions?
Just one clarification. The question also asked if the water will be interfering, but actually it will be beneficial, the water, because it creates better acoustic wave transfer. So
yeah,
actually
correct.
The water will be beneficial for the PSI method, the parallel seismic.
Exactly. For parallel seismic, we need to have a good acoustic coupling between the access tube, the parallel tube, and the pile. And water is a perfect conductor with a wave speed of about 1,500 meters per second, which is slower than the pile. So we can see a very clear separation of wave speeds in the parallel seismic. So this water field scenario is actually ideal. More questions? Okay, how about if the pile is getting a crack in the middle of the span? As I told you, unless we manage to get a cross-hole drill, the tests are not going to give you much information about the crack. If the crack is throughout the whole cross-section of the pile, and the waves cannot go through it, then we're gonna get some very limited or strange results from the parallel seismic, because the waves will probably get a very hard time traveling down. So it all depends on how large that crack is. More text questions. Okay, I'm afraid I can only answer English questions, but Mr. Zolfriki will summarize.
Yes, there are some questions. Yeah. I also sent you one picture, Gadi. Remember, you have ever sent me a nice picture about how to test the pile with
Yes.
doing you cut something and then you.
Yeah,
you
we presented that picture and we answered for that.
Yeah.
That was the
Yeah,
structure in the river.
I already presented before the picture. I don't think so.
We have presented the picture, yes.
Okay. How to test the pile that is under structure while the pile is together with the plot?
Yeah, is that the question of Mr. Yono?
Oh, you know. Yes.
Yeah. Okay, I have Google Translate. So let's say that we just have a reasonable translation. How do you test a pile that has been installed and old? After the plate has been knocked down, it turns out that the condition of the pile blends with the plate. So in this case, once we knock out the plate, the top plate of the pile, we don't really have the same scenario. We have a clear pile with access to the top. Maybe the top of the pile needs to be trimmed until we get some clean, unbroken concrete, but then we can go into normal testing with probably with the pulse echo method. Is this answering your question, Mr. Yono?
What is the difference? What's
the concrete blends with the pile? It's actually a very good situation. This is what is expected from a good construction. They have a good contact between the pile and the superstructure.
Eric, the last question, they're asking difference between testing with the PET and with the CHAM.
The difference between testing with the PET and with the CHAM?
Yes.
Okay. So these are two different test methods. The PET is actually a very quick, low resolution test with a limited information compared to the CHAM. So the advantage is that it's very low cost, very accessible, even in these scenarios, it's usually possible to do some testing with the PET. However, it's highly influenced by the superstructure, and many piles need to be tested in order to do some cross-reference. Alternatively, when under a superstructure, when testing with the CHAM, it's very, very tricky to drill the access tubes. If you manage to do that, you can get a very high quality test. If the question was referring to usual regular testing without the superstructure, then I would say that PET is a good test for small and medium piles, and CHAM is a better alternative for medium and large piles. For critical foundations such as high-rise buildings, bridges, things like that, where the pile is expensive, the superstructure is expensive, CHAM cross-hole testing is a much better alternative to PET because you need a high resolution and more information that the PET can give.
Okay, we have a couple of more pictures to share, okay? Just to bear with me. Let's see if I can do that. Window. Okay. This one.
I don't really see you.
It doesn't share? You don't see?
No.
Here?
Oh yeah, now something is shared.
Yeah, here you go.
Okay, so what we see here is we have a connecting, we have three, we have a couple of connecting beams probably on top of a pile. The pile is not visible in this picture. And when the top of the pile is going to be hit, on, I guess, on the center of that cross, the waves are going to go in all directions. The waves are going to go into the side beams and also down into the pile. And it's almost impossible to tell if the waves, the reflecting waves, are from the end of the beams or from the end of the pile. So what needs to be done is try to dig a little bit deeper, get a notch, and test a few piles for and try to get some repeatability. If we still get some information after we do that, that's going to be great. But again, this is really not an ideal case. Of course, if you manage to drill an access tube parallel to the pile, then parallel seismic would be a very good option. You can hit anywhere on the beams.
They asked again to explain this picture, which is what you just referred to as digging a notch inside the pile itself.
Okay, so what we have here is actually not a pile, but a column on top of the pile, and so we have no access to the pile, to the top of the pile, and no access to the top of the column. So what they did here, they did cut a small notch on the side, and we hit they hit that. We can see in the picture inside the notch there is the PET sensor, and to the left of the PET sensor is an area where they hit with a hammer, try to get the echo. Of course, remember that the waves are going to travel up just the same way that they are going to travel down. So all the limitations and caveats that I mentioned in my presentation about testing in this scenario apply.
And also there are a couple of more.
Okay, I can see another question from Anin. In dynamic testing, we still use 1D wave theory. Why not use a 3D wave theory instead? Well, what happens is that in dynamic testing and also in pulse echo testing, since we are talking about a slender pile where the length is much longer than the width, for example, more than the LD ratio would be more than 10. After 1 or 2 diameters, the waves become one-dimensional, and there's no point in going into the 3D theory in this case. Okay, Mr. Marini, what about skin friction from pile information? Can we get it, and how the test can be done in sheet piles? Okay, skin friction information is not something that you can get when testing under existing structure. It's over expectations. But when in a regular testing, when testing with the PET, the amplification can give you a good idea. The amplification that needs to be applied in order to bring the pulse back to a normal shape can give you some idea about the skin friction. Sheet piles cannot be tested because their L to D ratio is just too high for to get any signals, any echo from the toe of the pile. This was also a similar question from Andre. Could a test be performed in sheet piles? No. To know if there's a crack in the splicing joint? No. That's really way over expecting from any of these test methods. Okay, another question from Anin. Again, is in the pile integrity test, is it always must have a toe reflection? Well, if you don't get a toe reflection, you can still assume something about the top of the pile. If there was some kind of a necking or a crack on the first few meters of the pile, you would get a reflection from that. In cases where there is a lot of skin friction and there is no echo from the bottom, then this is the only information that you get. This is, of course, not a recommended case, and a different test method should be applied to very slender piles or when there is a lot of skin friction. More questions?
Just for clarification, someone asked if the test is for capacity. No, it's not for capacity. It's just for the condition of the pile.
Yeah. The only way to get the capacity is by load testing, either dynamic, dynamic, or static load testing. All the integrity testing methods are for testing the actual execution of the pile, how the pile was placed, if there are cracks, inclusions, or maybe it's shorter. To test the capacity is for testing the design, and tests that are for the design, as I said, are load tests. More questions? I want to remind you that all your questions are going to be summarized and answered offline when we have the time for that after the presentation.
There is still have any question from Pan in RS. You
Yes.
can see still about the theory of 1D wave theory, but
Where is that? In dynamics, 1D and 3D theory, I answered. Question from Anin Hudaya. What else?
Anything to do with pricing, you can offline discuss with Ulfriki from Indotest.
Yeah, it's really outside of the scope of this presentation to discuss pricing. Definitely, we are not going to start the bidding here on the presentation. Although this could be very amusing, this is not really the topic now. But please contact Mrs. Ulfriki offline.
Erez, last question. There's a picture that I'm presenting. Can you relate to that? Someone asked about how to test this scenario.
I don't know what's there. What is there?
It's not. There's not enough information there.
There is really no information there. So in order to test that, as I tell you, you start with some detective work. If this is an old foundation, an old building where the floor was cut, please try to get as much information as you get. We can't see anything there. We can just see maybe something that might be a connecting beam. We don't know if there is a pile, a raft, a footing, anything can go there. And without this information, your test is going to be a waste of money and time.
Oke. Thank you, Erez. Masih ada yang mau tanya?
Thank you very much, everyone. The presentation is going to be available offline in a while, and your questions are also going to be answered offline. So thank you very much. It has been a pleasure presenting to you. Thank you.
Ya, makasih semuanya, Bapak-bapak, Ibu-ibu.
Welcome.
Kita tutup ya Zoom kita siang ini. Alhamdulillah, semoga bermanfaat. Thank you everyone from Pile Test, from everyone, civil engineer from around Indonesia. We thank you for your participation. Good afternoon. Bye bye.
Good afternoon.
Welcome.